So let's start talking about organic chemistry. The first chapter is quite simple. It's actually more like general chemistry. So this is a little bit of a review. So I'm going to go really fast, okay, in this one. So pay attention. So first of all, origins of organic chemistry. Initially, the chemicals that were obtained from nature were the only ones that were called organic. So anything that's obtained from plants or animals were considered to be organic. Later on, it turned out that organic compounds were synthesized from inorganic compounds also, and therefore then the magic kind of disappeared. It's not natural anymore. It's apparently just a combination of certain elements together which give it organic chemicals. So now it's not really something about a vital force of nature, or not the fact that they're only found in plants and animals. It's just the way that the bonding occurs. It's a way of functional groups and so many other things. That is what is organic chemistry now. So what is it then? Okay, I didn't quite clarify it last in the previous slides. So here, organic chemistry is the study of carbon-containing compounds that are bonded with hydrogen, oxygen, sulfur, nitrogen, phosphorus, and halogens. If you look at the periodic table, you will find all of these elements on the right-hand side of the periodic table. The left hand are the metals, okay? And so the right-hand side of the periodic table is pretty much all the non-metals, and that's where you find all of these elements. The key element here is carbon, of course. Okay, you can have compounds of phosphorus and nitrogen by themselves, and they would not be considered organic. For anything to be organic, carbon is an important component in there. Carbon is found in group 4. It is the only non-metal in group 4. And the other ones are metalloids and then metals. Okay, carbon can be both covalent and ionic bonded with different things depending on what it is bonding with. It can combine with group 1 and 2, very stressful conditions, but it can do that, in which case carbon is going to be an anion because metals like to give electrons, so carbon will be C with a 4- charge on it. Okay, so that's the only thing it can do. Otherwise, pretty much everything with carbon is covalent bonded. There are some compounds that you need to be aware of that are not considered to be organic. So carbon monoxide, carbon dioxide, carbonate ion, bicarbonate ion, and then the cyanide ion. Okay, these are not considered to be organic. And we have so many compounds to talk about when we study organic chemistry. So it's a huge, huge, huge field, one of the biggest fields in chemistry. First, a little review of the atomic structure. Again, this is so Gen Chem 1. You know all of these things. The atoms have electrons, protons, neutrons. Proton and neutrons are found in the nucleus, and electrons are outside the nucleus. Atomic weight is the number of protons and neutrons in an atom, and that is found in the nucleus. The atomic number is the number of protons in an atom. That is also the identity of the atom. Technically speaking, in any kind of a neutral atom, the atomic number is also the number of electrons, okay? But we consider usually the number of protons as the atomic number. Isotopes are atoms with the same number of protons but different number of neutrons. Remember, neutrons are neutral, so if you change them, it doesn't really change any of the charges, okay? It just changes the weight of the atom. Electronic configuration is how the electrons are found in the atom, which means what regions they are found in. So they are found in shells, and they're found in specific regions in those shells. And the regions are called the SPDF, and you've done this again in Gen Chem 1. So just a little bit about this because we need to talk about this in organic just a little bit. Okay, so S is the lowest energy, which can have 2 electrons. P is higher in energy than S and can have 6 electrons. D can have 10 electrons, and F can have 14 electrons. The S block is the first 2 groups in the periodic table. The P block is the 6th of the main group elements. D block is the transition elements or the transition metals. And then the F block is the lanthanides and the actinides, which you find at the bottom of the periodic table. That's by energy. The shape of these regions is S is spherical shape. It has only one shape. P is a dumbbell shape. It has three different shapes going in three different directions. D has five. So the more electrons it can have, the more complicated the shapes get. Okay, and then F can have seven shapes. Electrons are usually filled by energy level. That is it. That is plain and simple, by energy level. If D has low energy than S, then you fill D first, and so on and so forth. Okay, so just because these are written out in certain way doesn't mean that's how you're going to fill it. Okay, we fill it according to the periodic table. So in any case, electrons are filled by energy level, and electrons are placed in these subshells in opposite spins. Okay, so you need to look at these three rules again. If you've forgotten them, I'm sure you'll find it in your Gen Chem book. Okay, so just to go a little bit over electronic configurations again and how to fill electrons. The first shell has two electrons, which are only in the S. The second shell, which has the 2s and the 2p, the 2s has two electrons and p can hold up to 6 electrons. That's what you have. And again, we are filling this by energy level, which means that 1s is lower than 2s, which is lower than 2p. So as we go outside to the shell numbers, the 1, 2, 3, then the energy gets higher. S is lower than p, and so on and so forth. Okay, so you fill out electrons this way. For bonding, as you would remember, there are two kinds of bonding, which is covalent and ionic. Ionic is transfer of electrons. Covalent is sharing of electrons. Covalent is only in the nonmetals, whereas ionic is metals and nonmetals. For most of the organic chemistry, we'll be focusing more on covalent bonding because carbon is a nonmetal, and all the elements that are bonding with it are all nonmetals as well. So we'll be focusing more on covalent. However, there will be a little bit of ionic as well because there is a whole section in organic chemistry called organometallic chemistry. So when the metals come in play, then you start having ionic bonding. Okay, so we'll talk about that when we get there. One last thing, or first thing about bonding, is that you have to draw them as Lewis structures, in which you show the electrons as dots or as crosses. And remember, when you show electrons, these are only going to be the valence electrons, not the core electrons. We don't worry about the core electrons, and you know how many valence electrons there are by looking at the group number. Here are some examples of Lewis structures. Again, these are not new to you. These are all old stuff, and this is how you draw the electron dot structure to show the sharing of electrons. And the nice color coding here will help you to understand how the electrons are being shared, which electrons belong to which atom. Okay, so for example, here in the nitrogen, nitrogen has the blue electrons and hydrogen has the green ones. Okay, and here oxygen has the pink ones and the hydrogen has the green ones. So it shows how the electrons are being shared. Now, typically we don't draw structures like this. We draw them like this in the lines. So we represent a pair of electrons in a line. Again, this is all Gen Chem. So you show these electrons. The electrons that you can show as dots are pretty much the lone pair of electrons. Okay, so for nitrogen, it's one. If you draw lines also, that is fine. It's not wrong. We're just used to seeing the dots, but lines are also fine. I draw both the things. I draw dots as well as lines. Okay, you can do whichever one you want. One thing to remember, which is really helpful as far as bonding is concerned, so that you never get any structure wrong, is to remember how many bonds any element should have. So hydrogen should have only one bond, carbon 4, nitrogen will always have 3 bonds, oxygen will have 2 bonds, and all the halogens will have 1 bond. Okay, so hydrogen and halogen 1 bond. What that really means is that hydrogen and halogens will be found as terminal atoms, terminal meaning at the end, whereas you find oxygen, nitrogen, carbon as central atoms. Okay, so they can be one of the central atoms depending on how large the structure is, but hydrogen and halogens will be found terminally. Now, hydrogens will never, ever, ever, ever be in the middle. Halogens, on the other hand, can be, and you have to be ready for that because there are some exceptions. Okay, regarding the number of bonds, these are the number of bonds they should have to have a stable octet. So you can have less or more, and if you have less and more, then you have a formal charge. Okay, so first of all, covalent bond, this is sharing of electrons. Again, Remember, the goal for any kind of bonding is to get the stable octet. We will talk about it later that there are some exceptions. Okay, but covalent bond is sharing of electrons. Again, you want to read up more, pick up your Chem book. The covalent bonds are divided into two: nonpolar covalent bonds in which the electrons are shared equally, and the polar covalent bonds in which there is an unequal sharing of electrons, okay, which means one atom is more greedy than the other one, which means that it pulls electrons towards itself. And how do we know something pulls electrons towards itself? It has to do with electronegativity. And so the more electronegative an element is, the more electron it will pull. And this is only in a bond. Okay, so for example, Cl2 by itself will not show any kind of polar covalent bond because both Cls are the same electronegativity. Okay, so you won't see anything in these kind of atoms, in the homotopic diatomic atoms. But as soon as you start having two different kinds of atoms, then there is a possibility. In that case, you have to look at the electronegativity chart. And if there is a difference of electronegativity of more than 0.5, then it is going to be a polar covalent bond. Now, do you have to remember these numbers? No, you don't. It's sometimes you just need to estimate and compare. That's the most important thing. You show a polar covalent bond by drawing an arrow in middle of the bond. Okay, so here Cl, in case of hydrogen chloride, Cl is pulling more electrons towards itself, and so it gets a slight negative charge. That's what the delta means, and the delta positive means that the hydrogen has a slightly positive charge, and this is because of unequal sharing of electrons. This arrow over here on top of HCl, this is dipole moment, which we have talked about in a later, or we will talk about this in a later chapter. Okay, all right, so this one here, this shows the distribution of charge. So dipole moment is a measure of polarity. Again, we will go through this one a little bit later also, because this we have to talk about this one in depth, okay, what the dipole moment is and all that. But here's an electronegativity chart. Again, as I said, you don't need to remember these numbers. There is no point. It's a good idea to go ahead and subtract a few of the bonds. So for example, do a few of the bond subtractions or electronegativity subtractions for carbon, hydrogen, carbon fluorine, carbon chlorine, carbon bromine, carbon iodine, and then see how these numbers come out. Or you can look over here also. Okay, so for example, the electronegativity difference between a CH bond is 0.3, which really is not that much. And that's why the CH bond is not polar, okay, at all, whereas the CF bond, it's quite polar. Okay. Formal charges are assigned to atoms which have less or more of the assigned electrons. Okay, so the formal charge can be +1, -1. Usually it's not +2 or anything, it can be, but usually we deal more with +1s and -1s. Okay, and so calculating the formal charge is this formula over here. You take whatever atom you're looking at and find the valence electrons in there, and you subtract all the unshared electrons, okay, in there, and half of the shared electron. The unshared electrons are the lone pair of electrons, okay. So valence electrons minus the lone pair of electrons, and also subtract the half of the shared electrons, which means how many bonds you have essentially. That should do it. So here are some examples of calculating the formal charge. So for hydrogen, for example, the valence electrons are 1 for hydrogen, and how many electrons are assigned to it is 1 because that's the one it's sharing. Okay, I just count the number of bonds instead of trying to take the number of electrons it's sharing and then dividing it by 2 or whatever it is. I don't do that. I just count the number of bonds it has. So hydrogen has 1, and I subtract that, and so 1 minus 1, that's 0. For nitrogen, the valence electrons are supposed to be 5, and that is coming because it's in group number 5. The assigned electrons are 4 because it has 4 bonds with the hydrogen, so minus 4. And so you subtract the 2. It has no electrons left over, by the way, and therefore the charge is going to be +1 on it. So go ahead and practice some more. See over here how the nitrate is calculated. The thing about the formal charge is when you see something like ammonium ion, NH4 plus, it's usually written just like this. And then you have to wonder, well, where is the positive charge? Is it on nitrogen or is it on hydrogen? So the whole exercise for calculating a formal charge is to figure out where that positive charge belongs, okay, whether it's on nitrogen or hydrogen. Similarly here, this negative charge, where does it belong on the nitrate? Does it belong on the nitrogen or the oxygen? Okay, that's what the whole deal is with calculating formal charges. This is a nice table. It's a nice shortcut to remember formal charges, and it works really well. Okay, so if you remember this, this will work really great for you. Okay, so for example, group 3, okay, which is boron, aluminum, and all that. And remember, boron is a nonmetal. And after that, you have all metals, okay, metalloids and metals. So group 3, not so much, okay, and you probably will not see so much of B minus, little bit you might, okay. But see here, because it has 4 bonds, it is not usual for boron to have 4 bonds. It has only 3, so it has a charge of -1. Typically for nitrogen and oxygen is really very, very clear, okay? It's very clear that nitrogen, for example, is supposed to have 3 bonds. So it can have 3 bonds in these different combinations, 3 single bonds, 1 double bond, and a single bond or a triple bond. In these cases, the formal charge is going to be 0, okay? But when it has 1 less bond, it has a charge of -1. When it has 1 more bond, then it has a charge of +1. And that's how it goes. Why so? Because if it has 4 bonds, it means it has given its electrons away. And if it's giving its electrons away, then it is positive. In the case of less bonds, it means it has excess of electrons because the electrons have not been bonded, and therefore it has more electrons and therefore more negative charge. Okay, that's how it goes for oxygen. Oxygen is supposed to have 2 bonds, so here is a formal charge of 0. If it has less number of bonds, it is negative. If it has more, then it is positive. It can only go 1 higher, 1 lower. Okay, that's how it goes. So that's how you should see it for nitrogen and oxygen. Halogens are the same way. 1 less bond, no bond, excuse me, no bond, and it's negative. 1 more bond, and it's positive. And the positive over here, you're going to see this very rarely. Okay, this is not going to be very common. So it'll be just like once or twice that you will see that in organic. Regarding carbon, carbon is a little bit unusual. Okay, that's why I'm dealing with it last over here. Carbon is supposed to have 4 bonds. Okay, and this is the combination for carbon. Carbon with 3 bonds can have negative, carbon with 3 bonds can have positive. So you really have to see how carbon is bonded and how the reactions are occurring to figure out whether carbon is negative or positive. So as we go through more chemistry, more organic, then you will kind of get the hang of it. Okay, this is a really good table to keep handy in the beginning. So as we talked about in the beginning about bonding, is that bonding is supposed to lead to stability. Okay, and stability for most elements mean the octet rule. Okay, which means that you should have 8 electrons in the valence shell. All right. So there are 3 exceptions to the octet rule. Okay, one is that there is an incomplete valence shell. Then second one is there is an expanded valence shell, and the last one is that there is unpaired electrons. Okay, so more electrons, less electrons, and a single electron. Okay, the way the bonding occurs is usually by pairing. Okay, and that's why the third one here, the unpaired electron, it is an exception. Okay, let me go through all of these. The incomplete valence shell is usually for group number 3 because it only has 3 electrons. So it can share only 3 electrons. And once it shares the 3 electrons, it is only 6. And therefore, this is incomplete valence shell. As far as the expanded valence shell is concerned, it's usually for covalent compounds which are formed from the third row elements. Okay, for example, phosphorus, sulfur, chlorine, iodine, etc. So anything from third row down, okay, will be the expanded shell. And the reason these form, if you remember from your Gen Chem, is that because they have the D shell, okay, and the D subshell is empty, okay, for these, and therefore they can have more electrons, okay, in them. So phosphorus, which is in group number 5, is capable of having 5 bonds, okay, over here. So normally it would form 3 bonds, just like nitrogen. So when it has 3 bonds, it has 1, 2, 3, 4 pairs of electrons, which is 8. When it has 5 bonds, and it's forming 5 bonds because it has 5 electrons to share, then it has a total of 10 electrons because 5 bonds, okay? Each one is a pair of electrons. So that is 2 more than usual. So phosphorus here also is more. Some of the other ones are sulfur and chlorine. So one thing you have to be aware of is that when you're drawing Lewis structure for sulfur compounds or chlorine compounds, in which those are the central atoms, then you have to take, you have to keep in mind, okay, that you can have expanded valence shells. So don't be afraid to draw 5, 6 bonds, okay, with these kind of elements. Just don't exceed the number of electrons that they're supposed to have, okay, which means that phosphorus is supposed to have only 5 electrons in the valence shell, so have only 5, okay, in there. Then you can share those 5 with chlorine or hydrogen or whatever. In summary, we have a few keywords and concepts to talk about. And please remember these things. Go over all of these things. Again, these are all Gen Chem 1, not even 2. Okay, so go over electronic configuration. Lewis structures are really important because we will still draw them in organic. Bonding, you still have to understand that. It never goes out of fashion. Electronegativity, all throughout organic chemistry or electronegativity will be our keyword. Okay, so literally you can answer almost any question, okay, with the answer electronegativity. Formal charges, once you learn how to do this, you will not forget it. Exceptions to the octet rule, this is probably the least important thing over here because we don't deal with phosphorus and sulfur as central atoms, but still, okay, you still need to know exceptions because in case you do encounter some compounds, then you should be aware of it, okay, and it should not take you by surprise. So that's about bonding and all.